false. Char is a Unicode character of 1,000,000.1 values, and int is a machine-sized integer. And then we've met the function types. Int arrow char is a function that takes an int and returns a char. And int arrow int is a function that takes an int and returns an int arrow int. By the way, I'm going to pick on you, David Feldman. I want people from California and who are working from home or working in the Hangout to send David ping if they have any questions. Okay. So you'll be my question broker. Yeah. So int arrow int is, as we discussed, shorthand for int arrow, the quantity int arrow int. It's a function that takes an int, returns a function that is int to int, and that is the currying that we discussed. But you can also define your own types, and that's where Haskell starts to get interesting. So let's talk about why you would define your own types. The first example is, or the first reason is because they're more self-documenting. So this type is called character, having nothing to do with char. It's a character in an RPG. It's got a name, a string, a gender, and a specialty. And we look at the show that it's derived, and it keeps all those fields in place, and we can work with it, knowing exactly what each piece is. The 8 there is the level. The string at the end is her specialty. She's a summoner. The second thing is, or the second reason, I can't get this to hide. Just go away. All right. The second reason is enumerations are an improvement over designated integers. So you've probably seen in C and Java where people will define a constant, where they say red is 0, green is 1, blue is 2, and then use those constants when they want to say make this thing red. But those are just integers under the hood, and there's nothing preventing an integer like 3 getting passed in, which doesn't correspond to any useful color.
So numbers correspond to those colors, just with the way that that's defined right there?
So, okay, so the C Java way of doing that is where people will define the constant red to be 0, and then use the integer 0 to specify a color. In Haskell, you can define a data type called color that just has values red, green, and blue, and not have to worry about those numbers.
Okay.
Under the hood, they are probably represented, they're definitely represented as some integers. It could be 0, 1, and 2. It could be something else, but the compiler takes care of that for you and makes sure that some junk value doesn't get passed in. Increased safety is another thing that you get when you define your own type. So here's a module where we've got a data type called length, which is kind of like a double, but has, the only way to get into it is to specify units. So, an API for a physics function might require a length. You can't just pass in 3 because, it's going to say like 3 what. And in this case, that allows you to document whether you intend your length to be 3 meters versus 3 feet. And that is that seems like a stupid, silly bug, but billions of dollars have been lost on projects where I think it was the Mars lander in like the late 90s, where one group was using English system units and the other was using the metric, and they didn't know that the other was using the other units, and things blew up.
How does this where construction work exactly? Like, how is that tied together?
Oh, that's okay. So that's module. It's defining a module. I haven't gotten into modules yet, and I probably won't for a while. Although you'll see it in the lab. But it says module units. So it's a module called units that exports those 4 functions.
Mhm.
What it doesn't export is the length constructor, which turns a double into a length. So you can't, the module encapsulates that process and prevents you from saying, you know what, I want 7 without a unit as my length, if that makes
Okay.
sense.
And also, David N just told me there was a big echo in the audio feed. I don't know what you can do about that.
What can I do about it? I can turn off the
Audio.
yeah. Turn off the microphone.
Well, not the microphone. I want to hear you.
No, because I need the microphone. I don't know why he's getting an echo.
Ask him to turn off the
You want to turn off
his microphone.
your volume, or
My volume is at 0.
then I don't know. I was on there.
His
It's
microphone.
okay.
His microphone.
Oh.
His microphone.
Okay,
He's got it. And one other thing, if you go back 2 slides before,
sure.
one more. The deriving show, what exactly is that?
I'm going to show you that. That's something I'm going to discuss in about 5 slides, I think.
All right.
So the 4th reason to define your own types is to increase your security. Many of you have seen this XKCD. If you have an API to your SQL capabilities of your module that only accepts a SQL sanitized string, and the only way to get a SQL sanitized string is to pass a string through the function sanitize, that will guarantee, in a way that the compiler can check, that all of your strings have been sanitized. And that's just scratching the surface. So those are some things you do with user-defined types. And we'll get back to a lot of these concepts. The syntax is up there. You have a data declaration. There's also type and new type, which I'll get into later in the course. For now, we're just going to work on the ones that are defined with data. Data, then the name of the thing, equals constructor, then 0 to infinity type arguments, and you can use a bar to separate multiple constructors. So for example, bool could have been defined as data bool equals true or false. In fact, that's exactly what it is. It has 2 constructors, one called true, one called false. And char, although I haven't put this up there, has 1,000,000.1 constructors, 1 for each character. So up top we have some basic enums, and then we have a union type called int or char, where it's either an int tagged with an I or a C tagged with a char. So there's 2 constructors, I and C. One takes an int, one takes a char. They both live in that type. And we have data nullable int, which either has no int or it has an int and an int. It has the constructor an int and an associated int. And this is the deriving show piece that I mentioned. When you're working in GHCI, you almost always want your types to be printable at the console. And that requires having a show instance, because what the GHCI, or the REPL, as I'll often call it, does is it calls the show method on the return, prints that to the console. So if you define a data type, data foo equals basint or flux double, and then you do bas15 at the console, there's nothing wrong with that value. It's a correct computation, but GHCI is not going to print it because it's going to say there's no instance of the show type class. So if you add deriving show after it, then it will create a show instance. And that's a really cool thing, because there are a lot of type classes that are very straightforward to define, and using the compiler to do it is better than handwriting it. So if we have any Java programmers who have personally experienced having to write .hashcode and .equals and .toString, you don't have to do that stuff in Haskell, because you can just use deriving and it'll figure out a sensible way to do it. So here's a union type. By the way, you're going to see more of these lambdas at the left. That's my prompt at GHCI, and I can show you how to set your prompt to be a lambda if you want. We have data nullable int. Nullable is maybe a confusing term, so I probably should have said optional int It's either no int or it's one int. As we see, and by the way, if you guys could pull up GHCI if you have it open, it's just good practice to try all these things out that I'm doing and try to prove me wrong, try to find a mistake.
Do you have to import something to get like one int?
No, you do that data declaration of GHCI.
Right. But the one int. Oh.
So isn't there a built-in like option type?
There is.
Just
There-
or something?
There is a built-in option type, and I'm going to get to that. This is just pedagogical. You wouldn't actually define this type because there's an option type called maybe, which is about 25 slides later, that explains this.
So we're declaring one int right here, right? One int doesn't exist in Haskell until you've put that in the data.
The data statement or the data, yeah, that's correct.
And then the int beside it is saying that one int is an int, and then nothing beside no int says that there's nothing there. Is that correct? Is that understanding correct?
Yeah, okay, so no int is defined as a value in the nullable int type. So when I do :t no int, it says nullable int because it says that is a value in this type. When I do :t on one int is a constructor. And a constructor is just a function that's defined when you create the data type. So it's able to say, okay, I see the one int constructor. That's a function that takes an int and it returns a nullable int.
But no int doesn't specify say a noun value or something like that, right? It's just an empty constructor.
Exactly. That's for the case. That's like an NA in R. It's or a null pointer if you're dealing with pointers. It's when you don't have a value. It's a type-safe way to handle when you don't have a value, because in Haskell you don't have the possibility of anything being null, whereas in Java everything can be null, or at least all the object types can be null.
Another thing, the deriving thing affects all the things inside the at its left. Like I wouldn't have to say like no int deriving show.
No, you don't want to do that. You derive show on the whole type. Yep. And that's what we call type classes, which we're gonna really hit hard in lecture 5. So are there any more questions? Okay, great. So yeah, constructors. When you define one of these sum types, it's going to create one or more constructors. A null array constructor that's zero array is just a value in the type, as we've seen. So data color equals red bar black creates a value called red and a value called black. You don't have to do anything to create those values. They come for free when you define that type. Unary constructor is a function into the type. As you can see, you do this int or stir type, I of int or s of string, and you get a value. You get 2 functions, which are constructors. I, which takes an int to an int or stir, and s, which takes a string to an int or stir. And by the way, there are much better ways of creating these sum types than what I'm doing. I'm just showing the simple way first. With constructors, you can mix arities. You have red and green, which are 0 arity, and gray, which is 1 arity. It takes an int. Again, that's something we've already seen. And then we have product types, which represent groupings or records of data, and those can have higher arity. So here we have data int bool pair equals int bool pair int bool. And that creates a constructor, which is a binary function. Takes an int, takes a bool, returns a value in that type. And one thing I want to point out is that the constructors and the types actually live in different namespaces. So this collision that you're seeing is okay. When you define a data type with one constructor, you will usually give the constructor the same name as the type. And that means that you have a value called in bool pair, which is the constructor function. You have a type that is in bool pair, which is the type that these things live in, and that's totally okay because they're in different namespaces. Nullary and unary constructors, those are also in sort of a way a product type. The nullary case is a product of nothing. So we say data unit equals unit. That gives you a type with exactly one value. And that actually turns out to be useful, believe it or not. And then the unary product type would be a wrapper. You know, for example, the sanitized string that I was talking about could just be a wrapper around a string. And here we have wrapped int equals wrap int, defines a function called wrap, takes an int, returns a wrapped int. So an algebraic data type can also be a sum or union of product types, including the nullary or the unary product type. And the whole set of things together we call algebraic data types. So here's a type that represents an event. And that event could be an error. It could be a key press event, which is going to have a char associated with it, which is what key was pressed. And it's going to have a click. Or the third constructor is a click with two integers, which are the x and y coordinates of where the click happened. So in action, up top is the data declaration. We show the constructor functions that are automatically generated for you. And then if you do this at GHCI, you can see that the type of the key with the character Z is an event. So yes, any questions so far? Great. So with constructors, you're able to put values into these user-defined types. And then the question is, how do you get them out? And you use what's called pattern matching, which is the fundamental control flow construct of Haskell. And I had to summon pay attention cat because this is really important. This is sort of the core of how Haskell works in terms of control flow. So we have the case of expression. Case, expr of, and then a bunch of pattern arrow exprs, which represent alternative branches, depending on which pattern the expr up top matches. So on the right, we have fib n, where it's essentially functioning as like a switch statement in C. If it sees 1, returns 1. If it sees 2, returns 1. If it sees anything else, it returns fib n minus 1 plus fib n minus 2. These are the explicit semantics. Evaluate expr. No matter what, expr is always going to be evaluated. The other expressions down there may not be evaluated. If they don't apply, then they'll be ignored. In the same way that if you do an if then else and the Boolean condition is true, then the else branch is never evaluated. If that expr matches pat1, then expr1 is says returned. I should say that it's about that expr1. Yeah, expr1 is what's returned. If not, then pat2 is tried, and likewise down to pat n. And if none of the patterns match, it's a runtime error. So the simplest pattern matching rule is the one that pertains to constant patterns, like 0, which is that they only match that value. So 0 matches 0, and the case up top returns the string y. And then we throw 159 in there, and it's a match failure because it doesn't match 0, and there's nothing else that it can match. The second rule is that a lowercase symbol will be a variable. It's a free variable. And it's going to match any value. And if it appears in the right-hand side, then the variable in the right-hand side is going to be bound to that value. So the 0 case matches the first pattern, and we get a 0. That's the case 0 of statement. And then the case 1 of statement, well, it doesn't match the 0, but it does match the x because that's a free variable. That'll match anything. And it binds x to 1, so it returns 38. Finally, a wildcard is going to match anything, but it doesn't bind any variables. And you'll often see the pattern where one terminates with a wildcard to eliminate the possibility of runtime match failures. You're basically saying, okay, one of these branches is going to happen, and that's good practice because even if some of the cases are erroneous, it's better to fail with a useful error message than fail with a match failure and not know exactly what happened.
So unlike, say, like Erlang, the compiler won't enforce that every single sort of path is, like handled in some way.
The compiler will warn you, and you can set up your project so that compiler warnings are treated as errors, which I recommend doing. But it's not automatically rejected as incorrect code. So here's where it gets really interesting, because those 3 cases are pretty simple. But this is how we unpack constructors. When you define an algebraic data type and you define all the constructors, you also get constructor patterns for free. So in this event case, the pattern error, it just matches the value error. It's just a constant pattern. But you can have a pattern with key followed by another pattern. Call it pat1. And that's going to match the value key ch if and only if the value ch matches the pattern pat1, and any variables that are bound by pat1 are going to be bound in the expression on the right-hand side. So for example, on the left-hand side, we have patterns. Key C matches only one value, which is key C, because we could go one step down. This is essentially recursive descent on the data structure. The only thing that matches the constant pattern C is a C. Key underscore is going to match any key, any value that was built with the key constructor. But it's not going to match error, and it's not going to match anything built with click. And finally, key X is going to match key C for any character C, and it's going to bind that character to X in the right-hand side. So click pat1, pat2, it does the same thing. It has 2 patterns to check and 2 values to check, the 2 values in the click constructor. The only thing that is new is that if there's a variable bound in pat1 and pat2, so like the pattern is click xx, then that's an error because it says I can't call both these things x. Now if you want to stipulate, okay, I want to match click x, I want to match a click where the 2 values are the same, you'll do that with a Boolean guard, which I'll show you next. But for now, I thought I'd go through a demonstration in case this isn't clear. So on the left, we have a function called isEvent. I didn't give it a type signature. That's bad form on my part, but the type signature would be event arrow bool. And it does a case event of, and it goes down through the list. And I should point out that slash equals is the not equal function. I know some languages have slash equals is in place divide. That's not what I mean here. So I'm guessing that a lot of you probably already know what this is going to return. Does anyone, who thinks it's going to return true? And who thinks it's going to return false? Okay, I'm going to step through it. So event is key Q. It does not match error. It doesn't match that pattern because it's not built with the error constructor. So there's no match there. So it goes down to the second one, which is key K, with a free variable k. And that is a match. And it says, okay, so where the free variable, where I have the free variable k in the pattern, I have the value character q in my value. So it binds k to q, and in the right-hand side, you get q not equal to q, which is false. And so for a second one, is okay, click 4837. What do you guys think is going to happen there? Is it going to be false or true? Who thinks true? Okay, everyone thinks true, so that's good. Doesn't match the first, doesn't match the second, matches the third, does the binding, returns true. So this is sort of a quiz. I want people to vote on what they think the answers are going to be. So this one. Anyone want to defend true? That's false. Second one. Yep.
False.
Anyone think true? That's false.
True.
True. That is a real character, by the way. It's actually in the Unicode set.
So, question, that the key one is saying that the k could equal anything that is not q, right?
Correct. Correct. And if it is q, it still matches the key pattern. It just returns a false, which is different from not matching. Which I'll explain when I show guards. Guards are a way to add a Boolean condition and say, okay, don't match unless this condition is true, and then it'll go look at the next one.
And were you, like, sorry, for k, so that's, you can use any, so that's because it's a lowercase symbol.
Yeah,
Okay, so,
it's a free variable, yeah. If it's an uppercase letter, then it will look for a constructor of that name, like constructor pattern.
Could you have put the matching instead of key k key and then the character q there for that matching? Instead of setting the variable k in the left, could you have like directly put the key q?
That would be a different pattern because that would match only the key q.
Yeah, but could you?
Of course,
Oh, okay.
of course. Yeah, you can build up, you could do that. You can have nested patterns. I mean, because ultimately the k and the x and the y, the free variables, those are just patterns.
Mm-hmm.
That's kind of what I'm trying to get across, is that these are, just like data structures, they're built recursively.
Mm-hmm. Is car UTF-8 or some other UTF?
So car is Unicode, which means that there's 1.1 million values, the code points, and those are different from UTF-8. UTF-8 is a specific way of encoding it into ASCII, or not into ASCII, into bytes.
So is it platform independent, how it encodes that, or independent? Or?
So the code points are, and Haskell is built in a way so that I'm pretty sure that all of the string types that it has are going to be platform independent. I think the endianness and the UTF stuff they take care of. I do believe that data.text, which is what you want to use for high efficiency strings, I believe that that is UTF-16, but it doesn't matter. And if you want to get it as a UTF-8 byte string, you can. So the other thing I want to show is that the if then else is just a special case of case of. These two statements are completely equivalent.
I have a question about the order of evaluation. Let's say like you have two patterns for the same constructor, but so you put a wildcard one above the more specific one. Are they evaluated in the order they're defined?
Top down. So if you had a key wildcard above key k, then the key wildcard is the one that would match, and the key k would never be. It would be unreachable. Yeah. Yep. So this is a cat that's hungry for knowledge. This is sort of the lecture questions if anyone's got any. Okay, recover your attention span, yell at me, whatever you wish to do. If we've got a good flow going and everyone wants to keep going. Awesome. So guards in pattern matching are Boolean statements. They can use variables that were bound in the pattern, and they will make a pattern not match if the guard expression is false. So as we can see, the top pattern is n, which is a wildcard. That would match everything. But if age is not greater than 20, then it will fail and it will go down to the next one. So describe 35, it's going to say, okay, the first one matches and that's adult. Describe 1, what do you guys think is going to come out of that? Infant. Everyone agrees on infant?
That's what, so that it means everything else.
Yeah. Yeah, the wild card is sort of the catch-all. And then 17 is going to be teenager. Yep. This is probably the gnarliest of the slides. This is I call it the as pattern. That's what it is in Clojure. You actually use an as, but I guess it would be an at pattern in Haskell. This w at that is prefixed to the h:t pattern. So h:t is a list pattern that will match any list that is a cons. And if we recall how linked list works, everything is a cons except the empty list. W binds to the whole thing that the pattern matches. So what do you guys think we're going to get with the summarize function on the empty list? The first pattern, yep. Just an empty list, a 0 and a 0. And what do you guys think we're going to get with summarize on the list, the singleton 1? It's going to be the second pattern, but what's going to be returned?
List 1, 1, 0.
Yeah, that's correct. That's correct. Does everyone see why?
I just want to understand what this at.
Okay, so H matches 1 in that list, right?
Mm-hmm.
Because 1 is the head of that list. And T matches the tail, which is empty. And the sum of the empty list is 0. W matches the whole thing. That W at followed by a pattern says I want W to bind to the whole thing that I'm matching. So W matches to the entire list.
How does this work like for the matching purposes? Is the part before the at or the part after or both need to kind of match your construction? Like if you, I guess this is going to be a list. Like say you have something that, you know, like is it like it wasn't a list for some reason, right? Say like your type took things besides just lists. It was some other type that was maybe like lists or sets or something.
So we have an at pattern on something that doesn't match, you're saying?
Right. How is that match evaluated? Is it like?
It doesn't match.
Okay.
And I believe that the only prefix to an at is a free variable.
Okay.
So it doesn't change the semantics of the match. It just gives you a convenient variable to represent the whole thing.
Got it. Okay. And is the list like head tail syntax? Is that just built into Haskell for lists?
Sort of. I'll actually get to that because list itself is just another algebraic data type, but it uses the colon, which is called cons, as an infix operator.
Okay.
So I'll show that.
So can you define that for any data type? Or is that?
I believe so, and if not, there are language extensions, which is something I'll cover probably lecture 5 or 6, that you can apply to get that functionality. So what do you guys think is going to happen? Someone who isn't sure, speak up. If you're sure, just raise your hand. What do you guys think is going to happen with the third case? Is there anyone who has doubts?
guess.
Yeah, make a guess.
So it's going to be a list with the first one being 5 to
The whole
an array
list.
of 5 to 7.
Yeah.
Then the next one will be a 5.
Yep.
And sum of t is just a tail, right? It's the sum of 7, 7.
Nine.
Close. The tail is,
Oh, is that the rest of the list?
that's the rest, yeah.
Okay, all right. So then it's going to be 9.
Exactly. And that's the pattern matching cat. That's
Can you just go back to that one?
sure.
So W is basically just repeating the input that it received?
It's repeating, in this case, yes, because the at pattern is binding to the outer pattern. If you have a situation with like nested patterns, you could bind a variable to one of the inner patterns and it would bind to that. So it doesn't necessarily bind to the value up there, between the case and the of, but it binds to whatever pattern it's affixed to. I don't use this very much, so and I almost never use it in complicated situations because it can make the code very hard to read. But I'm covering it because I do use it occasionally, and you will see it in code. So are we?
I guess, are there any restrictions on the expression after the aths, or can you do any expression that?
Well, it's not an expression; it's a pattern. So one of the language wonk details is that Haskell has expressions, declarations, patterns, and types, and they all have slightly different rules. Patterns are things that look like values, as in they're built up like values, but they actually have free variables instead of concrete values in their fields.
Zach Daniel had a question before, didn't mention it. His question is about constructors. Are constructor functions exempt from the concept of no function in Haskell is multi-arity?
Okay, so when I say no function in Haskell is multi-arity, what I really mean is that a multi-arity function is just so an n-array function is a unary function that returns an n-1 array function. And if n equals 1, then it's a function that returns a non-function value. So when I say multi-arity functions don't exist, I mean they do exist as a syntactic convenience. But the language model itself, every function takes one value. Because with currying, you can make a function that takes 8 values if you want, just as a function that takes a value and returns a 7-arity function. So now I'm going to talk about parameterized types, which is when it starts to get more interesting. We want these nullable versions of int. Let's say maybe int is no int or an int of int. And what do I mean by nullable? Well, many languages have this null concept that represents the absence of a value, or what you initialize something to if you don't know what it's going to be yet. And that can wreak havoc on you at runtime in horrible ways that can cost you large amounts of money and make you cry blood and make baby Xenu cry. Haskell's default behavior is, type shouldn't have null. And if you want a nullable type, then you add a constructor to it, as we've done here. We have maybe char is no char, or a char of char. But that gets a little tedious, because then when you want maybe int, you're defining another data type, no maybe int, or a maybe int of maybe int. And if you're a Go programmer, you're stuck doing that because Go doesn't have generics. But in Haskell, you can generalize. This is a parametric type or parametric polymorphism where maybe A is defined as either nothing or just A. And what that parametric polymorphism means is that for any type A, there's also a type called maybe A. And just by convention, our concrete types are capitalized, so our int and our char and our string, and our type variables are not. So the A is a type variable. Did you have a question, David?
No.
Okay, I thought I saw your hand. So in this case, the maybe type has these constructors. Nothing is a value of maybe A for all A. And what that means is that every maybe type has a nothing in it as a value. Just is a function A arrow maybe A. You give it anything you want and it will return just that. It will return a value in the maybe type corresponding to that value. So here are some examples. Just C has type maybe char. And just false is a maybe bool. And nothing is typed as a maybe A because it doesn't have enough information to know what it's a maybe of. Either is a parameterized subtype. Either A, B has a left constructor that takes an A and a right constructor that takes a B. So the type of left false is either bool B. And so why is it either bool B? Like, why is there a type variable there?
False is bool.
False is bool, so that's why there's a bool on the left, but why is there a B? Why is there a type variable?
It still needs the right.
It's part of the constructor, right?
Well, yeah, we don't have the constructor right in there, so we don't know what that B is. It could be anything. There's a left false value in either bool int, but there's also a left false value in either bool char. So can you guys tell me why you get a concrete type with the one in the bottom?
It can only be one of two values. It's binary true or false.
Well, you're talking about the bool, but why is that expression typed as either char or bool?
This is really a case statement.
Well, yeah, it's really a case statement, but that's not quite the reason why. So what
is the most generic type that you can infer from that expression?
Exactly. So in the case up there, the most generic type is either bool B, but in this case, because the then branch and the else branch always have to have the same type, we know from the then branch that the left-hand type is char, and we know from the else branch that the right-hand branch is a bool. What it's actually doing is it's setting up constraints on the types as a system of equations and then solving them. That's what the type checker actually does. And it does it automatically, which is what makes it neat. You don't have to do this stuff by hand. Tuples are pairs and triples and tetrads, I guess, or quadruples. I don't know what you call them. And instead of creating like a pair or a triple type, you just have the tuple syntax at the bottom. A comma B is the type that holds an A and a B. C comma D comma E is the type that holds a triple. And there's nothing special about tuples. This is just syntactic sugar. So if the pair tuple didn't exist, you could define it with the data statement in the middle. And what we're used to seeing as int char pair, that could be represented in prefix notation with the comma operator in parens, and then int and char. And same with the case on the bottom, except it's 2 commas because it's creating a triple. So tuples exist for pairs and triples and quadruples up to, I think 62 is the limit. After that, they're like, okay, you really shouldn't be using a tuple, you should use records, which are going to be described later. Once you have like 5 or 6 fields, it just gets hard to keep track of what everything is. Using positional cues is no longer enough. Tuple size 1 doesn't exist. That doesn't really make sense. You're just taking your value and wrapping it in. I mean, I guess you could make a tuple 1 as a wrapper. But there is a 0 tuple type that's called unit. And it's got 1 value in it, which is also a unit. Now, it's meaningless in pure code because there's no information in it. There's only 1 value. But it's going to become important when we deal with side effects because the type signature IO of unit means I'm an action that is, it's the type of an IO capable action that does not return a meaningful value. And it's okay that it doesn't return a meaningful value because it's being used for side effects. So the pair has these associated functions, FST and SND. And as you can see, FST on the tuple 2 cats returns 2. And then the question is, or the point that I want to make is that using pattern matching, you could write these functions FST and SND like so. So as an exercise, would everyone like to write FST3, which takes the first thing in a triple? If this is insultingly trivial and you get it, then that's fine. But if you want me to check, I can look at. Yep, exactly. Yeah, you got it. I would call it, yeah. Oh, you want to do, I'm sorry?
So for the tuple and for the pair, there's 2. There's FST and SND. For the triple tuple,
You would.
3. Okay.
If you were writing those functions, you could.
Okay.
But usually you use pattern matching to destructure things like that. So.
Not the yet.
Okay. And, yeah, you've got it.
I didn't believe it. I'm just kidding.
Yeah. And you guys, I don't think you guys were here for the first one, but
No.
Yeah, that's.
Something like that.
Yep. So I'll show you the answer for those who didn't get it. Looks exactly like that. And finally, there is no difference in Haskell between what we think of as infix operators like plus and our prefix functions like mod or length or so on. If it's binary, it can be used either infix or prefix. To take a traditionally infix operator and make it a prefix function, you enclose it in parens. And to take a traditionally prefix function and use it as infix, you enclose it in backticks. And your infix operators are always going to be symbols, so no letters. It's going to be like pluses and colons and minuses and dollar signs and shit like that. The one on the bottom, we have our cons, which is a constructor applied to 5 and the empty list. And that is the same thing as 5 cons empty list, which is the single element list with a 5 in it. This infix prefix equivalence I'm talking about is purely notational, but it exists in types too. So the first thing that I'm showing is the use of the typically infix plus as a prefix function on 9 and 5. You get 14. And then the second thing I'm doing is I'm using the comma function on the character q and true and producing that tuple. And then I'm typing that thing, and usually you would see open paren, char, comma, bool, close paren, but you can also write it like that, and that works just as well. And the reason this is interesting and important is to signify that fundamentally your values and your types are basically trees. where the first thing in the tree is a tag that says what it is, and then the remainder are the fields. So it's actually very Lispy, but with a different syntax and with static typing, so that you don't go insane trying to debug things. At least not most of the time. Sometimes you do. This is a record type. It's, you know, when you get to a large tuple, it's much clearer to put labels on the fields that are in the record. You saw that with the first example. And a nice thing that you get for doing that is that when you do a data declaration using record syntax, you also get getter functions, which are another way, an alternative to pattern matching for getting things out of the type. So here we have a constructor point. It takes an A and an A and returns a point A. It's a parameterized type. But then we have a color and an X and a Y that will take that build-up object and select out that field. Another thing you get with record syntax is you get an additional syntax for creation. That's in the purple. Here we have a constructor called P3D, and we have X, Y, and Z in fields, and you can specify them in any order, and it will figure out what the right thing to do is. You don't have to use record syntax just because it's a record type. You could do P3D137 in the lower right, and that would also work. It just makes the code more clear. And finally, there's update syntax. Now, when I say update, we don't do in-place updates to records because they're not mutable. So what you're actually doing is creating a new record with the fields that you specified as being different changed. So that's what you see in purple, where we have this point, and then we say, I want that point, but with y equal to 500 and z equal to minus 1,000, and you get a new point. If the list type were not built in, you could create it. And this is exactly what it would look like. You have a nil constructor, a cons constructor that takes an A, where A is the type that it's parameterizing, and a list of A. And the recursiveness of it is fine. We do a lot of work with recursion in Haskell. We prefer it over for loops and such. Linked, this is the length function on one of these lists. It does a case of, if it sees nil, it's going to return 0. If it sees a cons, then it's going to say, well, it's 1 plus the length of that list, of the tail. And the existing notation for lists is just syntactic sugar. So up top, we have list the way I defined it. On the bottom, we have it the way it's actually defined, but with prefix operators. And then on the bottom, we have what's more familiar, where we say, OK, A in brackets, that's the type for a list of A's. Revisiting length, this is kind of what it looks like. You know, you match against the pattern. If it's the empty list, it's 0. If it's a cons, then you throw away the head because you don't care. It's irrelevant to the length of the thing. And you get the length of the tail and add 1 to it. This is a tail recursive implementation of that because what we have up top is O of n in space consumption because it keeps creating stack frames as it figures out the length. It can never throw away the context of the first call until it has gotten to the bottom. And if it's a million long list, it's going to have a million long function. It's going to have a million stack frames. And actually, Haskell handles that pretty well. It used to be with many of these languages that if your list routines were not tail recursive, they'd blow up at like 20,000. I did it with 1 million, and it still worked. It was just slow. So on the bottom, we have the tail recursive version, where we thread in an accumulator. I don't have time, it looks like, to go over this, but if anyone wants to talk about tail recursion, I'm around. But the fact is that that's actually not enough in Haskell, because we also have laziness. Now, that's not a big deal, because quite honestly, if your list is only going to be like 300 elements, don't worry about it. Just write the thing that's elegant and maintainable. But with laziness, there are some additional things that you have to worry about in order to make these routines run in constant space. And I'll go over exactly what they are. This is what length actually looks like in GHC 7.8. So it does use the tail recursion. That's what len ack is it's a, is that tail recursive? Yeah, I mean, that's what it's doing essentially, is it's threading through the accumulator so that it can eliminate the tail call. And it's using unboxed types, which I might get to late in the series. That's, for optimization, because your regular int is boxed. There's a compiler directive saying no inline. This is what optimized code looks like. Probably looks like gibberish, but it's not really that bad. Lists are homogeneous. So because list is a parameterized type, for every A, there's a list of A type. And the requirement is that everything in that list has to be in that type. You can't mix types in a list. So up there we have a list of int bool pairs, a list of maybe chars, we have a list of list events, and finally the empty list is going to be list of A for any A. And as I mentioned in the first lecture, string is just a list of chars, and it's not terribly efficient because with a linked list, you're creating a cons cell for every char, and chars are usually fairly small. So if you want a large string, if you're working with large strings and you want performance, you'd rather use data.text, which has been much more optimized. If you're working with byte arrays or blobs, you'll use data.byteString. And I'll probably be using those some later in the course. For now, when you're just learning how things work, just use the built-in string. It'll do fine. And that's Omar telling us, well, it looks like he wants food, and it's 7 o'clock, which is usually when he gets hungry. But that's telling us that we're done. So any questions that you guys have got? I do have to check my phone because I think my wife is pinging me. Do we have any questions? All right, any questions out in LA? So does this mean that I explained everything well and people are totally clear, or does this mean that I just lost everyone? And
either that or the subject is enough to confuse people so that you don't know enough to make questions. That happens often.
So I mean, do you guys feel comfortable with this topic? Like, do you guys feel like you're ready to write some, just very basic level Haskell code and use pattern matching to rip things apart? And good.
I think the concepts will make more sense once we start actually writing.
Of course.
them. It's kind
Of
of hard
course.
with the abstract examples to know like what you would use something for, or like what. Like I'm a little confused about the maybe in either examples.
Sure. So let me bring up. It's okay. Okay, so let me bring up. Oh, by the way, if you want to set your Haskell prompt to be something else, because it'll typically include all of the modules you've loaded, and after you've loaded like 6, it just becomes this like unwieldy monster. You can set your prompt to something like GHCI, or what I set it to is a lambda. So I just use the escape character 955 and a space, and that's how I get my lambda prompts. Now, with regard to the maybe,
Does that exist even after you exit, or is it a?
you can set it in your GHCI profile. We can talk online, and I'll show you how to do that. So with regard to the maybe type, and of course the int or no int thing, you would never do that because you would just use the maybe in practice. So as I showed before, like nothing has type maybe A because there's not enough context for it to figure out what that type is.
Okay, so yeah, I guess one thing I'm kind of just drawing on the link. So those already exist. Maybe and either types already exist. I
Exactly.
got confused about what was being defined from scratch versus what already existed. Because data is the way that you define new types, right? Data,
Yeah,
name, something.
that's one way. I'll go over the other way later on. But the other way isn't really that interesting to us yet.
Okay.
So yeah, I mean, and you get a function called just, which is a constructor. Constructor and function are the exact same thing. And you get nothing, which is a value that lives in every maybe type. And with the either, as I showed, like if there's only enough context to figure out, oh, it can't even figure out a concrete type. But if you have something like that, it can figure out that the left-hand type is a string, which is a list of chars, but it can't figure out the right-hand type. If you give it more context, like let's say that you have a list, of course, remember that lists are homogeneous by contract. It will be able to figure out the full type. It figures out the most generic type that fits the context that it has.
So maybe helps you figure out the type.
Maybe is a type that allows you to say, I might have an A. Maybe A is the type that says I might have an A or I might not have one. It's basically an optional value. It gives you a null. It's a type-safe way of handling null, because if you see a function signature like that, you know that it might return a maybe. If you see a function signature like,
so that means that it might not return anything.
it might return nothing. It might return the value nothing, which is not the same thing as returning no value.
Okay.
It might return a value whose name is nothing.
And for all intents and purposes, nothing is like null.
Yeah.
Okay.
So
It's-
like you can't dereference it and get an exception. Like you have to deal with it.
Yeah, you have to do a case of statement, and you could actually, there's a function which you should never use called from just. Oh, it's not in here anymore. Maybe it's in data.maybe. And that will allow you to say, okay, I want to take the just off. And that's sort of like dereferencing a null pointer. It will throw an error. But that is something you should never do. There is a maybe unpacking function called maybe with a lowercase that takes you give it a constant value in the type B, and you give it an A arrow B. And what it will do is it will map to the first value you give it is the default. If it sees a nothing, it's just going to return that value. And the second one is, the second one is a function into the return type. And then if you pass this like a just 18, it's going to call show on the inner B. So it's going to give you the string 18. Whereas if you give it a nothing, it's going to use the default case.
It's like null coalescing operator.
Exactly, exactly. I mean, if it didn't exist, the way you would define it is maybe opt equals case opt of just x to default.
Did you mean put two A's in maybe?
Yes,
Okay.
yes, because it's I'm creating a new function.
Function. Okay.
Default. And this should behave exactly the same as. The maybe function is just a way of taking out that case of block, but honestly, the case of block is fine too. The case of is essentially saying, okay, if you have an option, you have to handle the nothing case and the just case. So there are types that say this could have a nothing. You have to do something about it. And then there are other types that say no, I can never be a nothing. So it's a type safe way of allowing a limited null.
Okay. So maybe allows nothing.
Yeah. Yep.
Thank you.
Do we have any more questions? Of course. Thank you. All right. So I guess I have to